Okay, so welcome everyone to the database seminar at the University of Washington. Today we will continue our series on blockchain and Bitcoin, and Dylan will talk about smart contracts.
Yes, thank you, Dan. Welcome everybody. We have an exciting week. It's a smart week today. I'd like to first give a few credits to our friends from Blockchain at Berkeley. It was nice to get in touch with them and borrow a few slides with their permission. So please check out their video lectures, very informative on the blockchain series. With that, let's jump in. Smart contracts. Step one, contracts. A contract is an agreement. We tend to write it down, but sometimes they can even be verbal agreements between multiple parties, such that we want to agree on some transaction, some standard way of doing business. A smart contract takes that in the one more step by writing it down in a formal way, a different kind of formal than legal language, but actual code that encompasses the logic of the contract. Here, all the parties agree on a particular set of code, a program that encapsulates the meaning of a contract, and they use this to agree on what will be exchanged, who will get the land, who will get the money, and so forth. This is code that will be run by some trusted entity, some trusted execution platform. So today we're going to explore all kinds of applications of smart contracts, how they work, and we'll compare them, of course, in detail to Bitcoin, which we've learned a lot about as the first blockchain that really made major existence. There's a lot of details coming up about smart contracts, and in particular on a language and platform for them called Ethereum. If you have questions on specifics, it may be good to hold off until we reach a demo where we'll explore an application for voting. So pretty much verified voting for different parties that want to vote on a shared ballot. And then we'll, time permitting, we'll explore some additional features that are coming out in the future of Ethereum and other smart contract-like currencies. So with that, let's jump in. What can we use smart contracts for? Well, of course, there's a whole bunch of financial transactions. You even saw some kind of smart contract-like applications last week from Guna's presentation. We could, for example, want to exchange real property in the world, like land or car ownership. And, of course, doing this is a complicated legal procedure. Typically, in these complicated transactions, both parties will put some money in escrow that is part of their commitment to follow through with the transaction. And if some party decides to cheat, then there's rules for knowing when a cheat happens and the money in escrow goes away. So having a place where we can hold escrow accounts and write down those rules in a formal language is a really good use of smart contracts. Voting. Voting is a big one. You may have seen in the news some time ago that people have made headlines like, smart contracts present a new form of democracy on the world. Well, that's because they envision a platform where everybody can vote in a way that can't be tampered, that is verified, that is publicly visible on the blockchain, and that these would be governed by decentralized autonomous organizations. Organizations that are run completely by code and not by human laws, instead just code laws, contract laws. So there was one particular instance of that with the DAO. They happened to have a bug that lost a lot of money. So make sure when you write your smart contracts, you don't write them with bugs. We'll get into more of those security concerns later. You can make Ponzi schemes with smart contracts. Think about it. Any logic you want to write down in a contract is possible. So if you have a scheme in mind that will reward people for joining this Ponzi scheme, if new members join the Ponzi scheme, then you can write that down. And people have actually done this for fun. It was more of a joke thing, but people actually put real ether into it because they wanted to claim the title of King of the Ether. And finally, one other I'll talk about is cyber-physical interfaces. So smart contracts do run on a blockchain, meaning that all transactions are publicly recorded and known for everybody. Applications can listen on that blockchain to see when a particular kind of transaction occurs, so that if, for example, you pay money into your Airbnb account, then an application sitting inside a smart lock could listen for that and detect, oh, look, I've been paid for. I'm going to unlock for you. And now you have an automated hotel. Business of the future. So there's all kinds of other applications there, proving that you knew some documents at some time. There's gambling applications that are coming out, really a wide space. But rather than go out into a bunch of different case studies, let's learn more about smart contracts, and then you can imagine how these different kinds of applications are enabled. Okay, so how can we implement smart contracts? Well, from last week, you've learned all about the blockchain behind Bitcoin, and there is some logic that we can use Bitcoin for. So to an extent, you can do some smart contracts using the Bitcoin operations, but not all the way, because we know that the Bitcoin operations are not Turing complete. There's no way to use loops. If your application somehow requires loops, then you're out of luck with Bitcoin. Another barrier is that the Bitcoin transactions are deliberately timed to be too slow for rapid transaction applications. It takes about 10 minutes to mine a block. The difficulty is adjusted of mining in order to maintain that 10 minutes. For some transactions, you'd really like them on the order of seconds. And it'd be a pain if you paid for your Airbnb and then you have to wait 10 minutes for the door to unlock, right? And finally, the more advanced Bitcoin operations, apart from just taking SHA-256s of signatures, are mostly not supported by the Bitcoin mining network. There's only a few miners that support these so-called non-standard transactions. And that's because most miners are only want to support the core of like Bitcoin transactions, the common ones, not the advanced ones that may not have been tested as much. So the solution, of course, is to consider different languages and platforms for using smart contracts. Ethereum's the one we'll study today, but there's lots more coming out. Counterparty actually embeds metadata inside the Bitcoin blockchain in order to enable smart contracts. Codius is a more JavaScript-y one, and there's private ones coming out too. Okay, I'd like to talk a bit more about Bitcoin versus Ethereum because it's very easy to overlay the different concepts, and we need to know when they are different. So for one thing, Ethereum, this platform for smart contracts, is 6 years newer. You know, it's still evolving. People are solving problems and figuring out hard game theory questions. The distributed consensus, agreeing who will form the next block, that remains the same for now. They are both proof of work based. In order to add a block to the blockchain, you need to be the first one to solve a hard cryptographic problem, a hash puzzle. But in the future, Ethereum's moving to a different system called proof of stake. And I'd like to talk more about that at the end, because it is a very interesting future concept. The block mining rate is very different. Bitcoin's controlled to 10 minutes. Ethereum is controlled to 10 to 20 seconds. You know, much faster transactions. The mining reward scheme is a little bit different. So we know that the Bitcoin mining rewards, they're currently at 12.5 Bitcoins per block mined. That's a good incentive to mine a block because at the current rate, you'd earn, what is that, about $130,000 per block mined. That decreases as more blocks are mined and more Bitcoin is minted into existence through the mining process. Ethereum, on the other hand, has a constant rate of minting. For every block mined, there's a 5 Ethereum reward. So that means that the monetary supply is, well, infinite, technically. It will keep growing as more blocks are mined. But the percentage of new currency minted in Ethereum as compared to the total supply of currency in existence in Ethereum decreases, right? Because it's a constant 5 Ethereum per block. It's not an endless supply of new coin minted. We do say that the monetary supply is inflationary, but it is not hyperinflationary. And that is a stark difference from Bitcoin, which people really claim to be deflationary because there is a finite cap on the amount of Bitcoin that will ever be mined into existence. So these are different schemes. I personally believe that Ethereum's scheme is much more survivable in the future, as when Bitcoin stops minting new blocks, minting as many coins per block, they will have to turn to solely transaction fees and other incentives to keep miners mining. Okay, so that was a bit in-depth there, but feel free to ask me now or later if you have questions on the monetary policy. It's really interesting stuff. One last ramification of that is the transaction processing tip, so to speak. So the cost of doing a mining in Bitcoin, because the monetary supply is capped, you would say that the cost of mining a transaction really just rests on the miners, though they do get tips from the people who want to do transactions. Well, in Ethereum, because the monetary supply is constantly growing, when new Ethereum is minted, that reduces the value of the currency for everybody a little bit. Because if you add extra Ether, that's the currency of Ethereum, into the supply, then everybody's Ether is worth a little bit less, right? So you might say that the cost of transaction processing is a bit more distributed in Ethereum. Good. All right, I hope you've had your fill of economic theory. Let's start looking more in depth at Ethereum. Okay, so for Bitcoin, we know that every Bitcoin's history is explicitly tracked in the blockchain. You look at a particular Bitcoin, and you can see, oh, I earned that Bitcoin from Bob, who earned it from Alice, and Alice was a miner, and that Alice mined a block which newly minted that particular Bitcoin. Now, you can look through the history transactions and trace through the history of every Bitcoin. Now, for Ethereum, things are more rolled up and summarized, as Dan pointed out last week. This could be a bit more efficient. Here, every user has an account, and that account has a balance. The debits and credits from accounts, those are still in the blockchain. You could trace through those, but the history of particular Ether is not tracked in the blockchain. Rather, the exchange of balances is tracked. So a little bit of a difference there. We also have a new type of account. These external user accounts are what you and I might open up, and we would put our own money into them by exchanging, say, dollars for Ether. Contract accounts are accounts that are owned by pieces of code. Everybody can see what that code is. They see the code on the blockchain itself. And currency, so Ether, can be sent to the contract accounts from a user account or from one contract account to another contract account and held there until the contract, through its code, sends that Ether somewhere else. So now there's both types of entities, and even code can hold money in this way. A little bit more on these points. So the code that you upload to the blockchain as a smart contract really is stored there, along with any storage that it needs, any variables inside that code, and a unique address that the code lives at. Yes?
So I have a question about the account settings. Is the balance of each account public in that sense?
Yes. Yes, everything, yes. Well, in order for an account to exist, it has to be on the blockchain. Even if you want to make like a new user account, well, you would have to do an initial funding of that account by buying Ether from an exchange, right? So you would register an account and you would get transfer money to that new address. There's also a special kind of transaction for creating a new contract account. Basically, you create a transaction where the payload, the input to that transaction, is the code itself. And you send that to a special address called the 0 address, and that creates a new contract with that code at a new address that is given to you. Yeah.
So who are the customers so far? Do you know?
Customers of Ethereum. Well,
Individuals?
Yes. So going back to these applications, so all of these blue on text are hyperlinks, and these are links to actual applications out there. There is a company that provides chain of custody services for diamonds. There is an actual Airbnb company that did this. The banks are involved in this in some way. I'm sure you could look up the details of particular banks. There's all kinds of new startups. Joy Token is behind gambling. They want to create verified gambling with agreed upon source of randomness and the ability for developers to create smart contract games and so forth. Okay. All right, so we've learned about accounts. Let's learn more about the smart contract code that actually executes. Well, in order to execute code, we need a place to execute it, right? And here, this is very important. We have to agree on a place to execute the code that no one can dispute. A secured, well-defined place so that every execution can be trusted without trusting the other parties. This place is called the Ethereum virtual machine. Here I want you to think about a simplified version of the JVM. It's like that, an isolated, deterministic version of the JVM. The Ethereum virtual machine is a stack machine on itself. It has a bunch of opcodes that look like this. You push things onto the stack. You store things to memory. There is a space for memory. You check whether something's equal to 0. You do a jump. You can do a conditional jump with a loop, and then you get while loops out of that. There's all these opcodes, right? And you could write these by hand. You could theoretically write in this assembly-like language to construct smart contract code. But it's very limited for a reason, and that's because this code is going to be executed by everybody, and we want to make sure that there's no way to break out or there's no security problems here. We also want to make sure that every execution is deterministic. It produces the same output given the history of the blockchain and the inputs that go into a call to a method of a smart contract program. So here in this setting, a contract is a program which is a collection of state variables that are recorded in the blockchain and methods that are part of the code. A transaction that miners mine and users make and even contracts make, but only when called, is a method call. And that has this currency of ether attached. I'll talk about gas in a minute. And the details of the inputs and outputs of this execution are recorded on the blockchain. Let's walk through this in a bit more detail here. Yeah?
I have a question about the deterministics. So it's like an application is executed at different times. Will the outcome like become different?
There are some variables which depend on when the transaction is mined. So there is a mining process, and we'll see that in a moment. You can access the time at which a mining occurs and details about the miner, these kinds of things. But those are still deterministic. Just they change if different miners mine them and what block they're located in and such.
It's made deterministic through the consensus mechanism in the blockchain.
I was thinking like if the history, like you have more history, maybe some small changes like in the.
Yeah, but even if let's say that node mines some more block, that will not be accepted by majority of the nodes in the network. So only the longest chain will survive in that sense. So it is made deterministic through the process of consensus.
Yeah. We'll see a diagram in a second that may help. So say Alice wants to create a transaction. What is a transaction? Well, it's a method call pretty much, right? It's from Alice's address to a particular address. This could be another user account, or it could be a contract account, and in which case it's going to a method of a contract account. There's some details about gas that we'll talk about in a minute. You can transfer some ether with you. In this case, no ether is being transferred. Maybe all Alice wants to do is vote. Not every method call requires ether. Alice signs it with a particular signature. There's some additional data that is input to the method call, because method calls, they have parameters, you pass inputs. Okay. At some point, this transaction is picked up by a miner, say this particular miner. And the miner receives this transaction and says, okay, I want to mine this and earn a reward for mining it. Okay, so I'm going to take this input, I'm going to run it in the Ethereum virtual machine using the contract code at this address, if it's a contract account. User accounts are much easier. As a result, we get some output. I'll talk about gas in a bit. That output is here, and the miner will then put this transaction inside a block that contains a whole bunch of other transactions, grouping them together, just like Bitcoin does with Bitcoin's blocks of transactions. Great. Now, if the miner happens to successfully mine this block, they solve the cryptographic puzzle. They will add that block to the blockchain. And here, to answer your question a bit better, there are some variables that depend on the history of the blockchain, right? For example, the balance of Alice's account may be different depending on whether the transaction goes here or whether it goes somewhere later in the blockchain if other transactions have been mined first. So that's all resolved through the distributed consensus on the order of transactions. So the block is added. This is great. And now the whole network can see that, yes, a new block was added. We agree that this miner solved the cryptographic puzzle. They have the proof of work. They have the right to add a block, and this is the block that was added. And now we're going to verify their block to make sure they weren't doing anything malicious or messy by actually running the transaction again in their own virtual machine. So the transactions that go to the network, they're actually run lots of times. Everybody runs them in their own Ethereum virtual machine simply to verify that the transaction has occurred. And this is because we want an environment where you don't need to trust anyone, right? You simply run the code up. Well, I got the same output, the hash is checked, everything is okay.
So is this code responsible for updating Alice's balance in case Alice pays or receives money, or maybe pays money?
That actually isn't handled by the code. Alice would specify how much of her ether, her currency, to spend in the transaction itself.
Okay, so who updates the balance?
The balance, oh, I see. So the balance would be updated when the transaction is added to the blockchain. So once this is added, this transaction is there, but there's also, there's data structures inside the blockchain that rely on a variant of Merkle trees that store the balances of accounts at each point in the transaction history. So when the transaction is added, then the balance is changed.
So who implements the EVM?
Well, you could go on GitHub and view the code for the EVM. I don't remember who originally implemented it. Probably the founders of Ethereum.
The same repos and build it themselves and run it.
Yeah. We all agree on the code of the Ethereum virtual machine itself. And we do that by like checking the hashes of the bytecode and so forth.
And how do they make sure that the contract code is not malicious?
Well, I will get to that more in a little bit, but basically, well, for one thing, the contract code itself is public. it may be very hard to interpret because you're looking at assembly language pretty much, this bytecode, right? So maybe there's something sneaky that the developer did and they try to hide from everybody. Well, at worst, if it was a totally, I'm going to steal all your things contract code, then the worst you could lose is the amount of ether that you sent in value and a quantity called gas, which we'll talk about in a minute. So there are bounds on the amount you can use. And once you lose it once, you're not going to send more ether, right?
Or I can crash all EVMs.
So,
You want to talk about gas a little later.
Yeah.
Much clearer. Yeah.
yeah, it shouldn't be possible to crash the EVM, but if you discover a bug in there, then, well, you've broken Ethereum.
Create an infinite loop, and then the VMs never terminate.
That is a great, yeah, that is a great idea. We'll talk about that. So first, I want to give you a sense of the higher level programming language, and we'll walk through another example in more detail. But really, people don't want to program in this low-level bytecode. They want to program using loops, maybe even infinite loops, right? Now it's way easier to write an infinite loop because I can write while true. Well, here is a simple contract. It's in a language called Solidity. This is the most popular one. There used to be another big one that was based on Python called Serpent, but support for that has been deprecated. So this is really the standard, at least for Ethereum-wise, and other currencies that are Ethereum-like. So here we have a contract. It has a state variable, this line up here. This actually lives on the blockchain itself in permanent storage. So it's kind of expensive to put things there. But you can put a little bit of information. If you're willing to pay the right price, then you can put more information, right? This is a hash table mapping from addresses, that is user account addresses, contract account addresses, to, well, a mapping from keys to values, right? Basically what we have here is an address-specific key value store on the blockchain. There's a function to add a claim, so to speak. This could be a claim that Dylan Hutchison lives in the time zone Pacific Standard Time. And the key might be time zone, and the value might be PST for Pacific Standard Time, right? There might be things that I want to tell the whole world about, and I put them on the blockchain so everybody can view it. And they can view it via this getClaim function. So here I might call setClaim. Message.sender is a special variable that here message contains the details of me sending a message to this code. Method calls are like messages in this abstraction here, right? So this is my address if I call this. If someone else calls it, they'll call it with their address. Then we store a key and we put the value in the key. Now everybody can read that. To call this code, you need an actual transaction that will run the EVM, modify the state variable, put the new state variable on the blockchain, and then it's done. The getClaim, though, doesn't actually require a transaction because you're simply reading data. That's why it's labeled constant over here. So very quick contract there. Okay, let's talk about infinite loops. Yeah, we certainly could write an infinite loop, and then all the miners would try to run that infinite loop, and they wouldn't finish, right? That's a problem. We could just take down the whole Ethereum network by creating a contract with an infinite loop. And the worst part is, we can't even tell if there's an infinite loop inside, because then we would have to solve the halting problem. You know, there might be a very obscured infinite loop that looks like it's making progress, but it's actually not making progress. Okay, so how do we deal with this? Well, we have this concept of gas. This is a payment that we make for computation. Every contract requires gas, and gas is consumed by every operation performed in the contract. That is, each opcode, and perhaps if you're interested later, we can look at the cheat sheet of all the Ethereum virtual machine bytecodes there. And it's also consumed by using memory. And the memory consumption cost for gas grows exponentially larger as you use more and more memory. So you can't even exhaust the memory of the machines running this unless you pay a really, really high amount of gas. You would run out of gas before then. All right. And using this method, we can actually estimate how much gas a method call would require in order to run. Not all the time, you know, because we can't solve the halting problem, we can't tell whether a method call would require less than infinite gas sometimes, but there's some handy tools that most of the time in the real world, they can tell us of how much gas a method call would require based on what operations are occurring inside that method and what other calls the method is going to make and how much memory it uses and so forth. So what is this gas compared to the main currency of Ethereum, Ether? Well, we can actually exchange Ether for gas, right? We can use our money to pay for computation that some miner somewhere is going to perform when they run your code in the EVM. So we know we have an estimate of the gas required to call a method. The contract caller, that is somebody who wants to make the transaction, they say, I allow you to use up to a certain amount of gas from my budget, start gas. It's an upper bound. I don't give you permission to use infinite amounts of gas because you would drain my wallet and I'd lose all my money, right? So I'll say you can use up to this amount of gas, start gas, and I'll pay you a gas price per unit of gas consumed. I'll pay you, say, 5 Ether per gas. That would be really, really high. It would be more like 5 times 10 to the negative 6 per unit of gas. But there's some fee per unit of gas, right? And I could offer more money per unit of gas, or I could offer less. This is kind of like a tip, right? How much am I going to offer you to run my code in the EVM and put it on the blockchain? Yeah, so there's some incentives here, right? Basically, if we want our computation to run right now, like we really care about getting this computation, this transaction on the blockchain, then we'll give a high incentive, put the gas price really high. But if we don't care as much, we don't mind if it runs a couple days from now, then we give a really low gas price. It's the tip, pretty much, in Bitcoin. Okay, so stepping through this, at the start of a transaction, the contract caller loses an amount of Ether equal to the start gas times the gas price. When the contract is executed and added to the blockchain by a miner, they will use a certain amount of gas that is calculated according to the operations performed and the memory consumed. That will use up some amount of gas, and if there's remainder left over, that goes back to the sender and they get the gas back. So you just pay for what you use, right? But if you're stickly, if you try to say specify a max amount of gas that is less than the amount of gas required to run the code, then the miner will try to run your code. It'll see that it runs out of gas, you haven't provided enough gas, and then it will stop that execution, put the transaction on the blockchain anyway, and say, look, I tried to run this, I ran out of gas. Not my fault, I couldn't run it. I'm going to claim the reward for running this computation anyway, because I had to compute it. So here the miner, they get the gas that you paid, even though no transaction was performed at all.
But this assumes, so in order for a miner to claim the gas from the sender, the miner needs to be successful at inputting the transaction on the blockchain.
Yes.
Otherwise, you might think about a malicious sender who just attacks certain miners, makes them unsuccessful, and he just consumes their resources, and he will not. Other miners who do not see this malicious request will succeed in putting the transaction on the blockchain. So in other words, I can attack some of the miners without perturbing the entire blockchain.
Yeah, so you're almost describing a kind of published attack on the Ethereum network, and I'd like to talk about that at the end too. The attack relies on expensive contracts that contain code that takes a lot of time to execute. But
the question here is more technical. Why do we need two units, both the gas and the currency? Because ultimately, all that matters is that product, the price per. So why don't I say directly, this is how much money I'm willing to pay for running this contract?
because it's a nice abstraction. The gas is charged from your ether. It's used to pay for computation. You get the remainder of gas used back, and that's converted back to ether. In the end, it's ether to ether, but you have a nice abstraction that everybody can reason about in the middle called gas. Also, gas is well defined in terms of the cost of gas for each opcode. But the ether price for each opcode can vary depending on the gas price. So
the gas price is specified at the beginning of the request.
yeah. So the base gas price is set for the opcode, but different transactions can have different gas prices.
The gas price is set by the user who sent the request, basically in the form that how many ether per unit, and there is a fixed unit Mayer price for each opcode. So that's more.
And this abstraction also helps you, let's say you are a miner, right? You can decide to mine only those transactions that give you a certain amount of gas price, which means for amount of time you spend, you will be able to estimate how much money you will get. Right? So that abstraction is very important.
Yeah. The miners should also be on an equal footing for the most part. Everybody's trying to mine the next block on the blockchain. They're trying to solve cryptographic puzzles to do that. This is another kind of computation on top of it. And as long as it's not too expensive, then the computational cost of running the EVM on transactions is dwarfed by the cost of inverting a hash function and trying to solve the cryptographic puzzle. If that assumption is violated, there's a potential attack we can talk about later. There's solutions there. Yes?
So how can I be sure if the EVM, the miner are not malicious, not always charge the maximum gas?
Because the execution can be checked by anybody, including you. You can run the EVM yourself and see, well, when I called the contract with this history on the blockchain and the inputs that I provided to this code, it ran this operation, this operation, this operation, and consumed this much memory. Oh, it consumed exactly this much gas. And that's the amount of gas that the miner charged. And everybody agrees this is the amount of gas because the execution is deterministic.
I should set the maximum gas, I guess how it should actually cost. Otherwise, I cannot prevent anyone to charge too much gas.
I didn't quite follow, but there's
you need to execute yourself of this code, and then get the cost of that, and then set the maximum gas as that exact cost for executing this part of code.
If you can exactly calculate it, then yes. Remember, there are a couple variables that can change based on when the particular transaction is mined. And also, you might try to put your transaction in the blockchain at its current state, but before it gets added, a different transaction gets added. And now your execution will be different because it occurred after another one, right? So everything matters. The execution matters at the time the block is added to the chain in the order that the transactions are set. Okay, good. Okay, so with this, so I forgot to mention that because of this gas mechanism, in addition to avoiding the bug of an infinite loop, it's also very expensive to perform a denial of service attack, because if you try to create an expensive computation that a whole network has to perform, well, you have to pay for that with gas. And so you need to fund the denial of service attack, and you'll run out of money or the network runs out of computation. So with that, I'd like to move into a demo. Here we have the backup, but here we're going to go. Actually, I have it here. You can all see this. zoom in. Good. Can everybody read this or zoom in more? Excellent. So here I've opened an IDE. This is an online editor that is supported by the Ethereum community. It's called Remix. We have some contract code on the right. On the left, we have some various options for compiling this code and even running it inside your browser in a kind of test blockchain that only you actually see. There's some static analysis going on, but first, let's look at the code. We'll get some feel for the language features, what you can put in an Ethereum contract, and then maybe run around with it a little bit and play, depending on the amount of time we have, which may not be much time. Okay, so here we have a ballot. It's a ballot for voting. It's not so much a financial contract, but we have a ballot. Here we can create data structures with proposals. These proposals, they have some name. Say we want to vote on what day of the week we should have 590Q next quarter, right? We could vote on Monday, Tuesday, Wednesday, and so forth. We could put their names here, their vote counts here. The vote counts accumulate. Hopefully we don't exhaust an unsigned integer in votes. Yeah, we have all the methods down here. There's some additional ones. There's the address of the person who created the ballot. We might give them, say, the authority to be the ones who close the voting whenever, so only they can decide when the ballot is closed. Or we could have ballots that are organized differently, right? We agree on the code, and then the code is the contract. There's a map from addresses to their choice of who to vote for. The proposals themselves are public information. All of these are stored on the blockchain. These are the state variables, right? And finally, we have a constructor. The constructor takes the proposal names, say Monday, Tuesday, Wednesday. It will add them into this little array of proposals, and then create a new ballot with that as its starting proposals. And finally, there's all these methods, right? We can ask, well, who is the chairperson? Okay, get the address of the chairperson. And the chairperson was set to the address of the person who created the ballot. Who did I vote for? I forgot. Well, let's go see who I voted for. I want to make a vote. Great. I'm going to make a vote. Let's see if I already voted. Set my votes in the hash table of addresses to votes to the person I want to vote for. If I already voted, then decrement the one that I voted. If I then increment the vote of the person I want to vote for. Now these method calls, they're atomic, so to speak. They either run all the way and all the effects happen, or they don't happen at all. If there's some problem, here I don't think there can be any problem with this particular method call. But if there was some problem, then they would get rolled back. If it's an exception, then the sender would lose his gas, and that transaction would still go onto the blockchain, but there would be no effect.
So then it's kind of like the developer's responsibility to make sure that there are no bugs. Because otherwise they're getting charged.
Well, the contract caller's responsibility. But also the developers too, because if there's bugs, then hopefully people won't use the contract at all. And then the developer doesn't have their contract being used. But yeah, making sure that this is bug-free is important. So down at the, oh, I don't have it in this version. But if we wanted a method that only the chairperson, the creator of the ballot contract, can call, then we have to make sure that it will halt execution if anybody else tries to call it. If we forget that line of code, then the contract says something different from what we intended, and people can exploit that, right? And this is how the DAO, this decentralized autonomous organization from a few years ago, raised $150 million in crowdfunding. Then they had a blog. People exploited the blog, and they lost $60 million the next day. Yeah, so, the work is not done. You have to secure your contracts. Yes.
So if you think of traditional contracts, like people who sign the contracts need to examine the text, maybe in English, right? So right now it seems to become this program, and it seems the user's responsibility to check whether these smart contracts doing what the developer claimed to do or the user intended to do.
Yes.
So it's I think it's a question here, like is this kind of a language the right abstraction for end user?
There is a need for Cosette.
Yeah, if you could specify invariants along with preconditions and postconditions and then automatically verify them, that would be really useful here. There's a little static analysis tools here that warn you that about different circumstances. They could all say down here that, oh no, the gas requirement of this is potentially infinite. Maybe it isn't in practice, but it actually could be. If enough people vote, they could fill up a lot of storage, and then that costs a lot of gas.
Privacy is a big concern. Is privacy, and actually there are two concerns. One is privacy, the other is accountability, verifiability. Does this happen here too? Can I ensure that nobody can read my vote?
Accountability is given to you in this code. It's clear what address votes on which. You can look it up in the blockchain. But privacy is not. Not in this code. Everybody can see who voted. Yet, how might we address that? Well, there's a variety of ways that we might look at that. One way is for people to commit to their vote without revealing their vote. So I think this is actually used in practice too. They will take their vote along with a string that only they choose, compute the hash of that, send the hash to the voting server, the ballot contract in this case, and that will store the hash. Now from the hash we have no idea who the person voted for, right? But then after voting ends we say, okay, the vote is over. Everybody reveal your votes. And now they send the original votes and the string they chose. They send that to the ballot. The ballot says, "Oh yes, when you hash these, you get the hash that you told me about before, that you committed to. I agree that this was your vote in the originally."
Yeah, what I take from this is that smart contracts were not designed specifically for voting. Voting is just this open voting is just an example of how the smart contract would be used. But the emphasis is on the smart contract.
Yes, voting is a popular application. I would say that this is definitely one of the big features of smart contracts, but no, it's certainly not the only feature or the key feature.
On the accountability, could someone not just generate multiple addresses and vote multiple times?
Yeah, you could do that. In this particular code, you could generate lots of addresses and then vote from them, right? You could create lots of accounts with small amounts of ether each. So that is another way to fool this system. And there's various ways that we might combat that, say by only allowing a list of addresses to vote, or requiring some ether or something. Good thinking. Such good thinking, I think, that I don't even have to run this. You can take it for granted. I will run it just a little bit, because this actually does give you some idea for what is going on here. If I can move this up. So say I want to create a smart contract with Monday. And Tuesday. And I'm creating this from a particular address, the address of this account. I could do that. This went onto the blockchain. I lost a little bit of ether. I went from 100 ether to 99 point, right? And that's the gas that I lost in order to create this contract. If I look at the details of this transaction, I can actually see all these things. Okay. It was from this address to, well, the 0 address. It calls that the constructor, but it got a new contract address, right? It costs a certain amount of gas. I said this was my upper limit. That's how much I was willing to spend. It costs that much. And there's all these other things. The hash, the input. This input is really big because it actually contains the bytecode of the contract itself. So that's going up to the blockchain. And eventually, here's the input that I had to the constructor that went for the proposal names. Here's Monday. Here's Tuesday. And so forth. Yeah, so we could keep playing around this. I would like to go back to the presentation, though, because it looks like we have 6 minutes. And how do I? Maybe there? The screen went away. There's the present button. All right, so we'll have a few conclusions here. I'd love to tell you about proof of stake. Maybe we'll go a minute or two over. But I think this is a great introduction to smart contracts for y'all. An important point to emphasize here is that the computations here that we perform with method calls that are transactions, they are inefficient. They are deliberately inefficient. These folks at blockchain at Berkeley, they call this redundantly parallel because we actually perform the work multiple times across the network of the Ethereum miners. But it is an efficient way to reach consensus without needing trust for third parties. That said, if there are parts of your application that don't need to be publicly recorded and visible and agreed upon, then perform them outside the blockchain and just put the critical components that you need agreement on, you need trustless computation for as a smart contract. Okay. So bear with me for just a couple minutes here. I mentioned before that Ethereum was moving in the direction of proof of stake. It's a new kind of distributed consensus that the details are still being worked out. You can work on this in your research. It's exciting stuff. First, we know about proof of work. Proof of work says that the miner who gets to add a block to the blockchain is the first one who solves a cryptographic puzzle. All right, that works. It solves the problem. It seems to work in practice. It wastes about $5 million per day just in Bitcoin, not even Ethereum, but just in Bitcoin. That's the mining cost to the world. I don't know about you, but I'd like a better solution than that. Proof of stake is an alternative to that relies on you putting up a certain amount of your currency, your Ether, say, as a deposit. So here, the way that we decide who gets to add the next block to the blockchain is probabilistically determined, not based on who solves a cryptographic puzzle, but by two factors. First is age, the time that has elapsed since you have last mined a block. It's a little more specific than that, but that's a good way to think about it. So that if you just mined a block, you're less likely to mine the next block. Second is a stake. How much currency are you willing to put on deposit to support the infrastructure of the Ethereum network? If you put up a larger stake, then the probability that you will be the next one chosen to add a block to the blockchain is a little bit higher. But it doesn't go to 1, right? These things increase, but exactly how much they increase per unit of currency you put on deposit changes. Now, if you are chosen to add a block and you do add a good block to the blockchain, that's great. You get a little reward. You get your 5 Ethereum, right? If you do something bad, that is, you add a block to the blockchain, but it doesn't verify, right? you have a different output, and other people run the Ethereum virtual machine, they get a different result. Or say even worse, you actually try to add multiple blocks to the blockchain by going off of like 2 different tails of the blockchain. Then there are rules that you can encode in the system called slasher rules. Guna mentioned them a little bit last week, where if it can be shown that you have violated these rules, then you lose your deposit. So you're very disincentivized from cheating, because you lose the money that you put up. And this money is put up for some amount of time. You know, it's kind of like a long-term deposit. So here the concept of confirmation changes a bit. We say that a transaction is economically confirmed if a lot of investors would lose their deposits on histories that transaction is excluded. So different kind of confirmation. Instead of the 6 confirmation rules, we actually use a dollar amount. And people can decide, you know, what threshold is the right threshold for deciding that your transaction really is in the blockchain. All right, that's the major point. A cool extension of this idea, I think they're still working out some important questions here, is proof of research. We like research, right? This actually combines proof of stake with proof of work. Here, the proof of stake determines who adds the next block, but there's a proof of work component, not mining, not solving cryptographic problems, but actually doing useful research computations on the on selected distributed computing problems like folding at home and all your favorite crowdsourced research projects. So there's some really cool ideas here. I think they've got some game theoretic problems to work out, but you know, Gridcoin is something nice. And with that, I think it's a good time to take a couple questions and stop. I'm happy to talk more about the security aspects offline. Yeah.
I think we are running out of time, so we should stop here and talk to Dylan offline.
Thank you.